Today we get to start Unit 6. Pretty exciting. We're going to talk about an integral, okay? Remember when the year started and we only had 3 things to learn? Limits, derivatives, and integrals. We're on to part 3 already. That's pretty exciting. Anyway, here's a definition. Write it down. I'm going to integrate from a to b of the function f of x dx, and that equals the limit as delta x goes to 0 of the summation as I goes from 1 to n of f of c sub I times delta x. That's pretty weird. Pause and write it down, because then I'm going to keep going. Delta x is the width of the partitions, and n is the number of partitions. Okay? Now, this is what it's looking like. Here's my graph. Here's the function going up. And I'm going from A to B. Okay? What I'm really doing is the area under the curve. Okay. My goal is to find this. Okay? That's my goal. Is to find that area. Add it up. Well, it's not a pretty shape. Okay? So this is what I'm going to do. Is I'm going to draw partitions. Okay? And I'm going to have, you have C1, and you have C2, and you have C3, okay? And there are certain heights. So when you do f of Ci, that's the y value. Delta x is the difference between them. It's how fat your partition is. So you're ending up with these rectangles. And we're adding them up. But we're taking a limit, because this delta x is going to get smaller and smaller and smaller. Because right now, if I did an area and just added up these rectangles, I'm forgetting all of this part right here is not included in my area, so I'm not very accurate. So what I'm going to do is draw extra partitions. Okay, so now my partitions got skinnier, and the amount of stuff that I'm missing is getting smaller. And if I go and divide them again, okay, they're really getting skinny. The amount being left out is less, and that's why we're taking the limit. So delta x is going to go to 0. It reminds us of when we were doing the tangent line and we were figuring out slope. You were using 2 points and figuring out the slope, and the difference between them approached 0. Okay, only this time we're adding up partitions. One day we're going to do Riemann sums, and they really are partitions. So the way to get a better accurate is to have n be huge, okay? So as delta x gets tiny and you're adding them all up, you're going to be more and more accurate. Today, all of our partitions are geometric shapes. Okay, so let's do this first one. Draw a graph of the area represented by the integral and compute it using geometry. So I'm integrating from 1 to 5. Oh, we didn't talk about that. A and B are the bounds, where you start. This is where you start, end. Okay, so this one I'm going to integrate from 1 to 5. So what's my graph look like? Well, 3x is a line with a slope of 3. If I put in 0, I'm here, right? You put in 1, I'm at 3. 2, 3, 4, 5. Here's 5. 5 times 3 is 15. So my line's going like this. Oh, that was a pretty bad graph. So there's 5. Thank goodness for markers. All right, my goal here is to find this area. Well, I'm going to turn it into a rectangle and a triangle. So if I integrate, my rectangle's 4 wide and 3 high, so 4 times 3. My triangle is 4 wide. Well, what's this? That was at 3. From 3 to 15 is 12. So 1/2 the base, which is 4, times the height, which is 12. And you end up with 36. Or you can do a trapezoid. You have this side is 3, and this side is 15. So it's the sum of the bases, 3 plus 15 divided by 2, times the width, which is 4, and you still get 36. All right? You always you're integrating from bottom to top. Left to right, you're getting positive area. All right? That's important, because we're going to talk about those properties in a minute. All right, this time I'm integrating from -4 to 0 of the line -5. Well, okay, so here's my axis. Here's -4. The line, this is y equals -5. So I'm looking for this area. It's just a rectangle. So it's 4 times 5, and you get 20, but it's negative. So it's negative 20 units. Why? It's below the x-axis. That's assuming you're integrating from left to right. Left to right, below the x-axis, you get negative area. All right, this last one here is the cosine graph. Oh, let's do it in blue. From pi over 2 to 3 pi over 2. Well, let's see. The graph goes like this. This is pi over 2, and this is 3 pi over 2. I said, well, what is it? Is it a semicircle? Well, sort of. So a semicircle is 1/2 pi r squared. And the question is, what's the radius? Well, from here to here is pi over 2, right? So you'd have 1/2 pi times pi over 2 squared, and you'd get pi cubed over 8. I said, but wait a minute, this distance is only 1, so I'd have 1/2 pi times 1 squared, and you'd get pi over 2. Okay, neither one of them are very accurate. So instead I said, well, let's try ellipse, and use this as 1, and this is 1, because an ellipse is pi times a times b, which are the two axes. So you'd have pi times 1 times pi over 2, and you'd get pi squared over 4. Well, currently, that's the best we're going to do. All of the things in your homework are actual shapes that are accurate, okay? So here's an example. This is a straight line, this is a semicircle, and more straight lines. They want you to integrate from 0 to 2. Okay, so it's this area right here. Well, how tall is that? That's 2. So it's a triangle that's 2 by 2 times 1/2, and you get 2. But it's -2. Why? It's below x-axis. Okay, if I go from 2 to 8, well, this is 2. What's that? 4, 6, 8. Is that 8? Yep. So what's my radius? Looks like it's 3. So the semicircle is 1/2 pi times 9. So 9 pi over 2. And then you're going to add 9 pi over 2 minus 2. And that's the best you can do. Oh, that was only 2 to 8. Sorry. Don't need that. We need that down here. From 0 to 13. We start out with negative 2, and we add 9 pi over 2, and then we have to figure out this one, which goes from what to what? 8 to 13. So that's 2, 4, it's 5 by, what's the height? 2 times a half, so that's 5. So you end up with 3 plus 9 pi over 2, and that's your answer. Okay? Not bad. Geometric shapes, use them. If it's below the x-axis, it's negative. All right. Some properties. If you're integrating from 0 to 0, I mean a to a, you didn't go anywhere, so the answer is 0. No width. Okay? A to b is the same as negative integral from, I'm going from b to a, is the same as opposite of a to b of f of x dx. If a is less than c is less than b, and you integrate from a to c plus c to b, is the same as a to b. All right? All right, if you're going to multiply by a constant, you can bring it out front. All right, and if you are adding functions together or subtracting them, it's the same as a to b of f of x dx plus a to b f of x dx. You need to, g of x, sorry. You don't forget the dx, that's representing the how wide the function is. F of x is the y value, is how tall the function is. Dx is how wide it is. All right? So let's use that property. They tell me if I integrate from 1 to 4 of the function, I get 10. From 1 to 4 of g is negative 4. And 4 to 6 on f is 5. They want me to integrate from 1 to 6 on f. So I could integrate from 1 to 4 of f of x and add to it 4 to 6 of f of x dx. So you get 10 plus 5 and you get 15. 4 to 6 means I'm going backwards, so it's negative, and you get negative 5. 1 to 4 of twice that, you just do 2 times negative 4 and get negative 8. Okay, and if I'm adding 1 to 4 together, you get 10 minus 4 and you get 6. Okay, all there is to it, integrals, the area under the curve, it's this great big limit function. Okay, I don't know if we ask you to repeat that or not, but we might, just like the definition of a limit, right? But remember that it's the area under the curve. If you're going from left to right, above the x-axis, it's positive. Left to right, below the x-axis is negative. If you're going backwards, if I integrate from 5 to 1 on here, this would be negative 6. If I integrated from 0 to 4, this would be positive 20. Think about that. Let it soak in. Rewind the tape. Listen to that again. Okay? All I've got for you. Do the worksheet.